Assalamualaikum warahmatullahi wabarakatuh. Good morning everyone. You can hear my voice ya? Boleh dengar
Yes, can hear.
Okay. Alright. So this week kita akan masuk chapter 4. Saya lupa nak update the e-learning actually. I just updated, baru saja saya update tadi untuk chapter 4. Saya dah masukkan slide ya, tapi as I mentioned to you in the previous weeks, the slide ni when I present to you, sometimes ada correction and there are some additional information. So normally at the end of the lecture, at end of next week, I will upload a new slide again if there is any update. Okay. So for the time being, you can use the one that I have uploaded in the e-learning. Okay. Alright. Before I forget, untuk kelas hari Khamis, for the Sunday class, we are supposed to have class on Sunday, 4 to 5 p.m. kan? But I think for the fasting month, for bulan Ramadan ni, can we just shift to Tuesday, 10 a.m. boleh sebab because I have normally hari Ahad saya ada kelas pagi 3 jam, so bulan puasa ni letih sikit lah kalau pagi petang ada kelas kan, so can we just tukar hari Khamis just for the bulan puasa, boleh
Boleh doktor.
Can, doctor.
Alright. Okay, thank you. So we will proceed with our lesson today. Yes, ada soalan ke? Ng Wei Feng, you raise your hand. Any question? Tak ada. Okay.
No question.
Okay, so this week and next week we will do chapter 4. So chapter 4 is about heat effects, yeah? Okay, so these are the content and the topic outcomes. Alright, so we are going to learn about the different types of heat, yeah? So first you will learn about sensible heat, and then under the sensible heat we will also do the heat capacity. So how to calculate heat capacity. Yeah, so we are covering constant volume heat capacity, constant P heat capacity. So yang atas ni CV and below is the CP. And then also the T, the temperature dependency of the heat capacity. Okay, after that we will do latent heat. So you will learn what is latent heat. So there are different types of latent heat, and then we will do the calculation and estimation. And then we will also do standard heat of reaction. So this is basically the heat that you have when you have chemical reactions, yeah. And finally, the heat effects of industrial reactions, which is basically the combination of all the different types of heat effects. Okay, and these are the topic outcomes. You are expected to be able to differentiate the different types of heat effects and their importance in chemical engineering, and then calculate the enthalpy change, delta H, for ideal fluids at given conditions, and then construct the hypothetical path for enthalpy change calculation, calculate the heat transfer, and then apply the enthalpy calculation in the energy balance. Okay, so before we go into the actual content of chapter 4, let me just give you some overview, and probably you have learned and you already know about this, so just a quick revision, yeah. Okay, so in physics and chemistry, heat is energy transferred from one body to another by thermal interaction. Okay, and the transfer of energy can occur in a variety of ways, among them conduction, radiation, and convection. Heat is not heat is not a property of a system or body, but instead is always associated with a process of some kind and is synonymous with heat flow and heat transfer. So heat dia bukan property. Apa maksud property? Contoh property tu temperature, pressure, internal energy, that is property ya. Tapi heat ni kalau you tak ada any change to the system, you will not have heat. So heat tu is always associated with process. Like there is a change in temperature ataupun there is change in the molecular structure, baru you boleh ada heat. So it's not a state property. Yeah. And then transfers of energy as heat are macroscopic processes. Heat can be measured by calorimetry, and the SI unit of heat is the joule. So dia is similar with energy. It's considered one of energy, and that's why the unit is joule. Okay, so this scientists outlined four stipulations for the definition of heat. It is something which may be transferred from one body to another according to the second law of thermodynamics. It is a measurable quantity and thus treated mathematically. It cannot be treated as a substance because it may be transformed into something that is not a substance, for example, mechanical work. So heat is one of the forms of energy. Okay, so heat transfers from high temperature to low temperature, and it can increase the internal energy U. And heat can also produce work, can change the kinetic and potential energy. Yeah, so when you have this system, when the heat transfers to the system, you will have positive. But when the heat is released, then it becomes negative heat. Okay, this is also related to, the heat from state one, the transfer of heat, which I think you have learned in energy balance or in thermodynamics. And also the energy balance, yeah, which relates between the internal energy, the heat work, and then the kinetic and the potential energy. Okay, this is related to first law of thermodynamics, which is the apa tu? Energy balance, yeah. Okay. I will go back. Right. So the first equation is the general equation for energy balance. So the change in heat plus change in work equals change in internal energy plus change in kinetic energy plus change in the potential energy. So let's say when you have a substance, and there is no kinetic and potential energy, then you can remove these two parts. So you are left with this one. And then for the the substance, yeah. So in this case, we only consider the PV work, the expansion or the compression. So in this case, the work term here becomes PdV lah, negative PdV. Okay, because you have the equation W equals integration of negative PdV kan. Okay. So because of the this comes from the definition of enthalpy. Okay, so enthalpy is U plus PV. So you substitute the equation for U here. First we differentiate DH. Yeah. So differentiate, we get this. Okay, and then you will get this equation. And then for constant pressure, so constant pressure means dP equals 0. So we can we can remove this term. You are left only with this one. And then this is for DH. When you write for DU, it becomes like this. So in this case, we can write Q equals delta H because ini tadi kan the previous slide tadi. Mana tadi? Ini ya. So you akan dapat samalah dq dia akan jadi du plus pdv, and here you get delta h sama dengan du plus pdv. So that means q equals delta h. Okay, for constant volume process, you can remove this term here because dV equals 0. So you are left with dH equals du plus vdB. So in this case, the heat becomes delta U, change in internal energy. Okay, so that was just some revision. Yeah. So for this chapter, we will learn about the different types of heat. Okay, so we have under the heat, you have sensible heat, the latent heat, heat of reaction. So this heat of formation and heat of combustion can also be categorized under the heat of reaction lah, because formation and combustion, there are types of reaction, chemical reaction. Okay, so we will first learn about the sensible heat. Okay, sensible heat. What are the criteria or the characteristics of sensible heat? For the sensible heat, there is no chemical reaction involved. Okay, no composition change, and no phase transition. So it only involves in the change of temperature. Sebab tu nama dia sensible heat. Sensible ni maksud dia apa? Sensible ni kan maksud dia macam logik lah. So bila you ada temperature change, katalah suhu tu berubah daripada, let's say, from 50 degrees Celsius to 100 degrees Celsius. So secara logiknya, of course there are heat involved. That's why kita panggil dia sensible heat, sebab dia melibatkan perubahan dalam temperature. Okay. But in this case, there is no reaction, chemical reaction, no composition change. Composition ni maksudnya kalau composition maksudnya katalah asalnya you ada satu saja substance, and then lepas tu dia bercampur, mixture contohnya. Tu dia ada composition change. And no phase transition. So phase transition ni maksudnya kalau daripada solid phase, let's say dia berubah kepada liquid, then itu ada phase transition lah. So no phase transition, so maksudnya perubahan tu berlaku dalam fasa yang sama. Kalau dia gas sahaja. Kalau dia liquid only. If solid only. Okay. The second type is the latent heat. So latent heat is the heat when there is a change in phase. Katalah you berubah daripada liquid kepada gas, which is the kita tengok kat sini . So from liquid to gas ataupun vapor, it's a evaporation process, right? So in this case, we have the heat of evaporation. So the heat of evaporation here, dia berlaku dekat temperature yang constant. So you can see the graph here, the temperature remains constant. Bila dia dah bertukar, 100% becomes vapor, baru dia ada increase again in temperature. Okay, so latent heat, dia tak ada perubahan temperature, but it involves the change in the phase. Okay, sebab tu kita panggil dia latent. Latent ni maksud dia macam it's not obvious, it's not latent ni macam tersembunyilah direct meaning dia. Okay, so dia tak ada perubahan suhu. So kalau tak ada perubahan suhu, macam tak ada heat involved kan, tapi actually dia ada heat involved. That's why nama dia latent. Okay, and then the third heat is the heat of reaction. So this is heat in chemical reaction lah. So when you have formation or combustion, when you supply heat to get the chemical reaction, so this is under the heat of reaction. Okay, so first we go to the sensible heat. All right. Okay. Okay, so first we look at the internal energy. The molar or specific internal energy of substance may therefore be expressed as a function of two other states variable. So these may be arbitrarily selected as temperature and molar or specific volume. This is actually from saya dah explain sebelum ni. When you have when you have a substance, pure substance, and it's in single phase, sama ada dalam solid, dalam liquid ataupun dalam gas, then you can just select two properties. Yeah, bila you fix the two properties, all other properties will be determined as well. This is what it means by the degree of freedom equals 2. Yeah, remember kalau you ada single phase and it's a pure substance, then your degree of freedom is 2. Meaning that you can fix two parameters, properties, and the rest of the properties can be determined from that two parameters. So in this case, katalah kita pilih T and V, temperature and molar volume, to represent ataupun to calculate the internal energy U. So from this equation, so kita boleh tulis dia macam ni lah, U equals U in the function of T and V. Okay, so from this equation, you can do the differentiation, dia akan jadi macam ni. Yang ini saya tak boleh nak explain lah because this is mathematics, purely mathematics. I think you have learned in differential equation punya course. So when you do the equation, the differentiation, yang ini dia akan jadi D, the normal D, and then this is the partial differentiation lah because you have two factors kan. So it becomes du dt at constant V times dt, and then plus du over dv at constant t times dv. Okay, and then from the previous, I think you have learned this is actually from chapter 2, but in chapter 3 we explain briefly in the ada bahagian depan sikit tu kan yang pasal constant volume work, constant pressure process tu. This is from the definition of CV lah, okay, constant volume heat capacity. So you can replace du over dt at constant V ni with CV. That's why it becomes CV times dt. Okay, so you have this equation. Now we can set the second term here. Kita boleh set this term becomes 0 under these two conditions. Okay, condition yang pertama, when it's a constant volume process. So in this case, dv equals 0. So sini jadi 0 lah. So you boleh potong, boleh buang. Okay, and then the second condition is when the internal energy is independent of volume. So this can be applicable. It is true for the case of ideal gas. Okay, so for ideal gas, dia punya internal energy does not depend on volume, and also for the case of incompressible fluids. Apa incompressible fluids? Basically liquid lah, because liquid when you compress the volume, dia tak berubah banyak kan. So we can consider liquid as incompressible fluids. Okay, so under these two conditions, we can remove the second term. So dia akan jadi macam ni. So you can rewrite the, yang ini penerangan constant volume ya. Okay, so whenever the internal energy is independent of volume, regardless of the process, this is exactly true for ideal gases and incompressible fluids, and approximately true for low pressure gases. So untuk low pressure gases pun kita boleh approximatekan dia sama dengan ideal gas, but it's not 100% accurate lah, but you know it's still acceptable. Okay, so in this case you can rewrite the equation as this. So du equals cv dt. So kita boleh kira you can transform back into u, delta u, by doing the integration. Okay, so in this case delta u equals integration from T1 until T2 cv times dt. Okay, so the second process is when you have constant pressure process. In this case kita consider pula enthalpy, okay, H. So let's say the H now we express in terms of temperature and pressure. Okay, so again you do the same thing again, you do the differentiation. Okay, and then because of the definition of CP yang ini, so you can you can replace with CP kat sini, and then also we consider it's a constant pressure, so this term becomes 0. Okay. Okay, so the two circumstances allow for the final term to be set equal to zero. Number one, for any constant pressure process, regardless of substance. Number two, whenever the enthalpy of the substance is independent of pressure, regardless of the process. This is exactly true for ideal gases and approximately true for low pressure gases. Okay, so samalah, you are only left with this term, so you can do the integration to get delta H. Okay. Moreover, Q equals delta H for mechanically reversible, constant pressure, closed system processes, and for the transfer of heat in steady flow exchanges where delta EP and delta EK are negligible and WS equals zero. Yang ni tadi saya dah tunjuk dalam introduction tadi, yang ini. So when you have constant pressure, constant pressure depan lagi. Ni. You can derive this equation for constant pressure. So delta H now becomes Q. Okay, so you boleh calculate the heat from the change in enthalpy lah. Depan sana. Yang ini, okay. So in this case, it is applicable for mechanically reversible, constant pressure, closed system processes. Closed system maksudnya tak ada mass in, mass out, okay. And then it's a steady flow exchanges where EP, delta EP, change in potential energy and change in kinetic energy are negligible, and WS equals zero. So WS is defined as the shaft work. Apa contoh shaft work? So shaft work tu work done by contohnya propeller or turbine ataupun pump. Okay, so in this case kita tak ada shaft work. So for this case, you are only left with this term. Okay, so you can write Q equals delta H, which is equals integration of Cp times dt. Okay, now first, if you want to calculate the Q ataupun delta H, you need to know the equation for Cp. Sebab Cp ni is actually it depends on temperature. So you need to determine the temperature dependence of Cp baru you boleh integrate this equation, right? Because you cannot assume that Cp is constant unless it is stated. Yeah. So for normal condition, Cp is usually a function of temperature. Okay. So first we need to know the temperature dependence of the heat capacity. Okay. So these two equations here are the most common expression for Cp. Yeah, so you can either express in terms of alpha, beta, gamma, or ABC. Alpha, beta, gamma, ABC ni they are all constants. Yeah, and they are characteristic of the particular substance. So it depends on the type of substance. Value dia will akan berubah lah. Okay. Now, let's say if you combine these two equations, we can combine and then we can rewrite the constant ataupun parameters dia as this. So you have capital A, capital B, capital C and capital D. Okay, yang tadi ada A dia tak ada T and then you have BT and then you have CT squared which comes from here and then DT power negative 2 which comes from here. Okay, so in this equation, either C or D is zero, depending on the substance considered. So we just write. We want to express in this equation so that you can apply generally for any types of substance. Okay. Right. So for ideal gas heat capacity, we just add this superscript Ig untuk tunjuk dia adalah for ideal gas. Okay. And the values of parameters ABCD, okay, this ABCD, you can get the values from table C1 of appendix C for a number of common organic and inorganic gases. Okay, and then the two ideal gas heat capacities are related by this equation. So let's say if you want to calculate CV, you can calculate from Cp, meaning you calculate Cp first and then you use this equation to determine Cv. Okay, so in this case, for the Cp Ig, ideal gas, okay, kalau kita nak calculate dia, you have to refer to appendix C. um, okay, let me show you Appendix C. Okay, this one. All right, so this is Appendix C, heat capacities and property changes of formation. Okay, so you have here table C1, heat capacities of gases in the ideal gas state, and then you have C2, heat capacities of solids, C3, heat capacities of liquids, and then C4, standard enthalpies and Gibbs energies. Yang ni nanti kita akan guna semasa the heat in chemical reactions, ya. Okay. Ini dia lah. Okay. So this table is for you to find the values of parameters or the constant A, B and A, B, C, D. Okay. And they depend on the chemical species ataupun substance. So you boleh cari apa nama species, nama substance dekat sini, and then you have the chemical formula. And then this is the Tmax, meaning that the maximum temperature that you can apply this equation yang ini, ya. Alright. And then you have the Cp Ig over R value at 298 okay, betul lah, 298 Kelvin is given here. And then here you can find the A, B, C, D. Yeah. So tadi in the slide I have mentioned to you that for the different substance you can only have either C or D. So kalau dia dah ada value C, dia takkan ada value D lah. It can only have either one. Yeah. And just be careful for B and C and D. This value here is stated. For example, B kan, ini ialah times 10 to the power of 3, and then this is times 10 to the power of 6. Later I will show you an example so you can see lah macam mana nak guna the values. Yeah. Alright, so the first table C1 is for ideal gas. Okay, and you can also you also have for the solids. Okay, so yang ini untuk solid, and okay, for solid dia ada A, B and D only. Okay, and then you have the heat capacities of liquids. Okay, so for liquids you have the A, B and C. Alright, so be careful when you know when we give you a question. First you must understand, you must know whether that substance is in gas, liquid ataupun solid. Because otherwise you will choose sometimes you may choose the different heat capacity values. Okay, so for gas you must refer to the first table lah, C1. Okay, so this is Appendix C. Okay, example 4.1. Example 4.1. Okay, so this is the same question as in your textbook, yeah? The parameters listed in table C1 require use of Kelvin temperatures in equation 4.4. Equations of the same form may also be developed for use with temperatures in degrees Celsius in Rankine or in degree Fahrenheit, but the parameter values are different. The molar heat capacity of methane in the ideal gas state is given as a function of temperature in kelvins by this. Okay. Okay, so you are given this equation as this. Okay, asal-asalnya tak ada lah ni. So saya dah conteng. So actually the first number here, it corresponds to the value of A, and then the second number is the value of B. So yang ini saya sebut tadi, you have to be careful because dalam table C1 tu dia tulis 9.081 and then the up there it writes 10 to the power of 3. So in this case you have to apa tu? Untuk cancel out tu you kena bawa letak sini negative 3 lah. Okay. And then for C it becomes here negative 6. Okay. Okay, so for this case you have to develop the equation of Cp Ig over R for temperatures in degrees Celsius. Okay. So solution, the relation between the two temperature scales is given here. So temperature in Kelvin is temperature in degree C plus 273.15. Okay, so you substitute this equation for T ni, capital T, replace with this one. So you get this. And you just kembangkan, okay, expand and then you can write for each term of T, okay, and then T square to get this. Okay, so you can see that the value of A, B, and C, they are different when you use different temperature scales. Okay, so now okay, okay. So evaluation of the sensible heat integral. So just now we learned about the Cp over R kan, but ultimately why we determine Cp is basically because you want to know the heat ataupun the delta H. So in this case you have this equation yang tadi 4.3. This is the equation for the sensible heat. Okay, so Q equals delta H equals integration of from temperature 1 to temperature 2 Cp times dt. Okay, so macam mana you nak calculate this Cp punya integration? Okay, we can actually express Cp. We can actually express this equation later in 4.7. So I will show you how we derive this. Okay. So, yeah. So you have this integration of Cp here in the equation for sensible heat. So macam mana kita nak evaluate ataupun nak calculate the Cp, we can conveniently use integration of Cp over R. Kenapa Cp over R? Sebab relation tadi yang ABCD tu dia dalam bawah dia ada R kan? So you have Cp over R. Okay. So we do the integration of Cp over R times dt. So in this case, kita masukkan tadi here the equation. Saya tulis balik. Let me just show you. You have Cp over R equals A plus B E plus Cd plus dt negative 2, right? So from here, when you take the integration, so you tambah je integration sini from T0 to T, okay, and then you have dt here. So you do the integration lah. Yang ni pun is just mathematics je, maths, okay. So A dia akan jadi AT, okay, and then BT and BT square over 2, seterusnya lah, okay. So you get, finally you rearrange, you will get this, okay, A and then, okay, first term, second term, third term and fourth term. And here we introduce this new parameter which is tau, okay, this is symbol tau, which is T over T0, ataupun kalau you ada temperature 1, temperature 2, you can write as T2 over T1. Okay. So we substitute into this equation. We can, yang ini kita keluarkan tau minus 1 dekat sini. So you are left with this bracket. Okay. And finally kita dapatlah yang ini. Okay, after some rearrangement, you boleh try by yourself. Ya, saya pun saya biasa kalau dalam kelas saya tunjuk sendirilah the derivation. Okay, so you are left with this equation, and then yang dalam bracket ni kita boleh kita boleh express dia as ni. Dia ada bracket yang macam segitiga tu, CP H over R. Okay. Okay, this is equation 4.8 here. Yang ini macam mana kita derive dia. Yang atas ni is basically somewhere this one T1 2. Okay. Yang equation atas is you just basically you substitute tau into the equation, you rearrange, you suppose you can get this equation lah, 4.7. Okay. And then for the 4.8 tu tadi, you have to rearrange like this. You have to bring out the tau minus 1 kat luar, baru you dapat this form. Okay. So for this sensible heat, you can either use this equation, either equation 4.7 or you can use equation 4.8. Okay. It's just that the difference is that when you use equation 4.7, you can just calculate this, and then once you dapat value ni, you just times R, because R ada kat sini kan, tapi dekat sini tak ada R, so you have to times R untuk dapatkan Q or delta H. But for the second expression, 4.8, you have to find this CPH over R, and then untuk dapatkan delta H tu tadi, you kena darab R, and then you need also to multiply the change in temperature. Okay, so that's the difference. Yang atas tu you tak perlu multiply with change of temperature because it's already included in the equation. But for the second type of equation, you have to multiply with the change in temperature. Okay, and alright, so when you are given T in the question, you can directly solve. Yeah, okay, katalah you nak cari delta H ataupun Q, so you will be given the temperature, so it's straightforward, you can just use the equation. But if you are given the heat and you want to find the T, then it will become slightly complicated because you have T on the left hand side and you have T on the right hand side, sebab delta CP ni dia dalam unit dalam function of T kan. So in this case, when you have the same parameter on both sides, then you have to solve by iteration. Okay, so a starting value for T allows for the evaluation of CPH, and then you substitute this value into the equation above to get new value of T, which from then you re-evaluate CPH, and we continue the iteration until convergence on a final value of T. Later I will show you an example. Okay. Now, so there are two types of the calculation of CPH, whether you use the integral form or you use this form. So we can express in this kind of equation. So yang integral CP over R dt ni we can write as ICPH bracket T0 T and then you have semicolon and then ABCD. This is just an expression, yeah. It's actually used for when you write the programming ke kan, dia guna macam ni lah. Okay, ICPH. And then the second type of equation, bracket CPH over R, is we are using MCPH. Yang dalam ni dia sama. Okay, so the way you calculate tadi is, okay, you have delta, Q delta H sama dengan 0T CP T. So if you use this first integral punya form, dia akan jadi macam ni lah. You kena darabkan R CP. Okay. But if you use the second form, dia akan jadi you have to multiply R CP H over R and then you have to times, yang ni ada darab times temperature difference. Okay. So yang ini tadi kita boleh write dia as ICPH. Yang ini kita boleh write dia as MCPH. So which one you want to use is actually it's up to you, ya. Ada orang dia suka pakai yang integral form ni. Okay, ada orang suka pakai yang the alternative form. For me personally, saya lebih banyak guna yang second form ni lah. Okay, example. Calculate the heat required to raise the temperature of 1 mole of methane from 260 to 600 degrees Celsius in a steady flow process at a pressure sufficiently low that methane may be considered an ideal gas. Okay. So, okay, so in this case, the solution is the same as the one given in the textbook, yeah. So you have the substance, species name there, methane, and then the temperature change from 260 degrees C to 600 degrees C, and you need to calculate the heat. Okay, so here you have the T0 initial, and then T final. So you can calculate tau. Okay, just remember to change the temperature from degree Celsius to Kelvin. Yeah. So you have the tau value kat sini, and then you need to do the use this equation. So in this case, dia guna equation yang ini. Okay. So you need to do the integration of T0 until T for Cp over R dt. Yang inilah this equation. Yang ini 4.7 ya. So you use 4.7. So you need to find the A, B, and C from appendix C, table C1 tadi. Okay, so you just substitute, masukkan tau, masukkan T0, and don't forget to times R kat sini. And you will get the answer of inilah, okay, in joule. So 19,778 joule. Alright, so in this case, the value of R is depends on what kind of unit that you want to express Q. Okay, so kalau you nak express di dalam joule, so you have to use the R in joule as well. Okay, I mean in SI unit. Okay. Alright, so this is example 4.3. as you can see here, okay, I just read the question. Yeah, what is the final temperature when heat in the amount of 0.4 times 10 to the power of 6 BTU is added to 25 pound mole of ammonia initially at 500 degrees Fahrenheit in a steady flow process at 1 atm. So this is actually from the old book where which is using the American unit. So if you use the current, I mean the 7th edition is in SI unit. Okay, so this is the question in SI unit. What is the final temperature when heat in the amount of 422 megajoule is added to 11.3 kilomole of ammonia, initially at 260 degrees C, on a steady flow process at approximately 1 atm? Okay. So, in this case, kita kena guna yang equation tadi untuk solve T, this one. Okay. So, there will be iteration. Sorry, yeah. Okay, so first, we need to find the value. So you're given the amount of heat for 11.3 kilomole. Yeah? So in this case, you can divide lah, the amount of heat divide with the mole number. Sebab calculation, the equation is actually for per unit mole. Yeah? Yang tadi tu soalan sebelumnya, kita tak tulis per mole kat sini because the question here already indicates 1 mole. Yeah, so you can apa? You can just omit the per mole here lah because it's already indicated 1 mole here. Okay. Otherwise, normally kita akan letak lah per mole because this unit is in per mole. Okay. Alright. So you have the delta H and the initial temperature is given, T0 is 533.15 Kelvin. And we want to know final temperature. Okay, so first we can find the values for constant A, B, C, D from the appendix. So you carilah ammonia. Ammonia dapatkan A, B, C, D. Okay, maybe I should saya tunjuk saya buka balik the PDF tadi, appendix. Okay, kita cari ammonia. Ammonia. Okay, ammonia and kat sini ammonia is here. Okay. Dia start daripada sini yang ini ialah, jangan salah baca pula. This is the CP at 298 Kelvin per R. Okay. So you have to take the value A here. Okay, 3.5 ni ammonia, nampak kenapa saya tak boleh nak? I cannot. I wanted to highlight this, but I cannot. Okay, never mind. So, the ammonia is here. Okay, so this is the value of A, 3.578. And then this is for B, 3.020. And remember, you have to times 10 to the power of -3. And then this is D. C tak ada D, negative 0.186. For D, dia akan jadi power 10 to the power of 5 lah. Okay. Alright, so going back to the slide. Okay, nampak how you get the values of A, B, C and D. So saya dah tulis dekat sini. Alright. So in this case, you have this equation. Kat atas lah pula, nampak tak? I think you can see ini. This equation to solve for T. Okay, so first you need to find the CP yang ini, yang bawah ni. Tapi kita tak ada, kita ada yang ini saja kan? Which is the MCPH. So we use this equation to calculate lah, 4.8. So in this case, C tak ada, so you can just cancel, you can just remove this third term. Okay, so you have only A, B and D. Okay, just substitute into the equation. Dapat dekat sini lah. This is the value CPH over R is 5.50 53. Sekejap yang ini, sorry. Yang ini saya okay. Sebab kita tak tahu kan. So you have to apa tu? You have to start with an initial value. Yang ini you just estimate by yourself. Okay. Dalam soalan tadi diberi, okay, initial temperature is 533.15 Kelvin ataupun 260 degree Celsius. So you can start with any value higher than the 260 lah. So let's assume 500 degree C. Okay, so assume T1 ataupun I just write this T1 lah. Kalau you write T0 pun tak apa. Okay, it's just a matter of writing. So let's say the initial temperature is 500 degree C, you convert to Kelvin. So now you can calculate tau. Okay, bila you dah dapat calculate tau, baru you boleh masukkan dalam this equation yang kat atas untuk dapatkan CPH over R. So the first value is 5.5053, and then this value kita substitute dalam ni. Okay. Of course, this one you kena times R, and then yang ini delta H tadi kita dah calculate from the previous slide. Ni, delta H, this is delta H ya. And then plus inilah T0. T0 kita tadi 533.15. So you get your T, your new T. Okay. So here the T is 1349 Kelvin. Okay, so now you use this new value of T. So sekarang ni T2 dia jadi 1349 lah. Dapat daripada sini tadi. From the previous calculation. So you calculate the new tau. Okay, calculate new tau. Tau, masukkan dekat sini lah. 1349 divide with 533.15 dapat 2.53. And then you recalculate CPH over R. And then you recalculate T. Ulang balik. Okay. So just repeat until you get a converge value. So in this case, I did until the 5th iteration. So after 5th iteration, we get converge value of T, which is 1252 Kelvin. So this is your answer lah. This is the final temperature. Okay. Sekejap, sama tak dalam textbook jawapan dia? Check. Okay. In the textbook, it's on page 135. The answer given is 1250. So kita dapat 1252. It's okay lah. It's acceptable. Just slight difference. Sebab dalam buku teks ni kadang-kadang the answer dia dapat tu daripada programming. By calculation using computer. So sometimes dia akan dapat jawapan yang lari sikit lah. Sebab kita calculate secara manual, right? Okay, so don't worry too much if your answer is slightly different than the textbook. Okay. Alright, so it's already 10:55. I think I should stop here until the sensible heat. Nanti petang kita akan sambung the other types of heat. So boleh ya, for sensible heat, again remember, it is caused because there is a change in temperature. So you ada initial temperature, final temperature. In that case, of course, there is some kind of heat akan terlibat. There is a change in heat lah. So in this case, that is the sensible heat, which is accompanied by the change in temperature. So in this case, you have to calculate the CP. Okay. So macam mana nak calculate CP tadi saya dah tunjuk lah. It's a function of temperature. Okay, so you need to find the value of A, B, C, D from the appendix C, and then you find the CP, and then from the CP baru you boleh dapat Q ataupun delta H. Okay. Any question? Alright. Okay, tak ada soalan So kalau tak ada soalan, we will stop here. And I will see you again in the afternoon. Okay. So,
Thank you, Doctor. Have a nice
alright.
day. See
Thank
later.
you.
Thank you, Doctor.
Alright. Thank you. Bye-bye. Jumpa lagi.